Section: Introduction. In this section, we will discuss how models like CLIP are trained to align images and texts, and how they struggle with longer texts. We found that CLIP performs poorly on text-only tasks, which is a problem for applications like text-image retrieval and image generation. To address this issue, we propose a new training approach that focuses on aligning both text-image and text-text pairs. By optimizing for both types of pairs, our model performs well on various tasks. Previous work has shown that contrastive learning is effective for training models in text-based tasks. Different methods have been proposed to improve text-image training, such as locked image tuning and modified loss functions. CLIP introduced the idea of contrastive text-image pre-training, which has since been further developed by other studies. Our model architecture includes a text encoder and an image encoder with the same dimensions. We use a BERT variant for the text encoder and the EVA02 architecture for the image encoder. By pre-training the model with masked language modeling, we achieve better performance compared to starting from a fully trained text embedding model. Our training approach involves 3 stages, where we simultaneously train for text-image and text-text matching tasks. We introduce longer synthetic image captions to improve text-text performance and use hard negatives to enhance the text encoder's ability to distinguish relevant text. This multitask training method helps our model maintain alignment between text and images effectively. Section Summary. In this section, we introduce the concept of contrastive training models like CLIP, which align images and texts using pairs of related data. We highlight the limitations of CLIP in handling longer texts and present a novel approach that optimizes for both text-image and text-text alignment, improving performance on various tasks. Our method involves training with large-scale image caption pairs and text pairs simultaneously, resulting in a model that excels in both text and image retrieval tasks. Section: Data Preparation. In this section, we discuss how we prepared the data for our model training. Our text pair corpus, which we refer to as C:(text_pairs), includes information from 40 different text pair datasets. These datasets are mixed up, and we randomly pick one dataset at a time. We then fill each batch with the embeddings of text pairs until the batch is full. For the first stage of training, we utilize the LAION400M corpus, denoted as C:(imgs_pairs), which contains 400 million image text pairs sourced from Common Crawl. In the subsequent stages, 2 and 3, we switch to using the shared GPT-4 dataset, C:(imgl_pairs), which consists of around 100K synthetic captions generated with GPT-4v and an additional 1.1 million long captions produced by a large captioning model trained on the original GPT-4v output, totaling approximately 1.2 million image captions. In the third stage, we introduce a triplet text corpus, C:(text_triplets), that includes challenging negative examples. This corpus combines data from various sources such as MS Marco, Natural Questions, NQ, Hotpot QA, and the Natural Language Inference, NLI, dataset. Each training batch comprises 1 positive item and 7 negative items, with the hard negatives selected using text retrieval models to emphasize relevance in text triplets, except for NLI where negatives are chosen randomly. Moving on to the loss functions used in all 3 stages, we employ a joint loss function that combines 2 info-NCE loss functions. For text pairs in stages 1 and 2, we apply the L_NCE loss function to pairs of text embeddings within a batch. This function evaluates the cosine similarity between a query and its corresponding target relative to all other targets in the batch. The temperature parameter tau influences how the loss function weighs minor differences in similarity scores, with tau set to 0.05. Similarly, for text-image training, we use L_NCE to calculate loss values for text-image matching, with the temperature parameter tau being trainable. In stage 3, For text-text training, we utilize text embeddings from the triplet database and an extended version of the L_NCE loss, denoted as L_NCE +. In each stage, the text and image encoders process inputs from the respective corpora, and the training involves different combinations of loss functions tailored to the specific stage. For stage 1, we truncate text values to 77 tokens to enable the use of large batch sizes. In stage 2, text values are truncated to 512 tokens, and synthetic data with longer captions is added to enhance text-text and text-image retrieval. The final stage focuses on fine-tuning using text triplets and hard negatives to improve text-text performance to match specialized text-only models. Section Summary. In this section, we prepare our data by utilizing a diverse text pair corpus consisting of 40 datasets, with shuffling and random selection for batch filling. We employ different corpora for text-image training in each stage, including LAION400M and share GPT 4V datasets, and a triplet text corpus with hard negatives for stage 3. Our training stages incorporate joint loss functions combining info-NCE loss functions, tailored for text pairs, caption-image pairs, and text triplets, with adjustable temperature parameters for similarity weighting. The training steps involve applying text and image encoders to specific corpora, using various combinations of loss functions, and adjusting batch sizes and text truncation lengths to optimize multimodal and text-text performance throughout the stages. Section: Evaluation. In this section, we assess our model's performance on various tasks involving text, images, and a combination of both. We compare our model's results with those of OpenAI Clip, EVA Clip, and Long Clip VIT-B16 models. We also include a comparison with another model for text retrieval performance. Our model demonstrates strong performance across all these different tests. To evaluate how well our model performs with both text and images, we use the CLIP benchmark, which includes tasks like zero-shot image classification and cross-modal retrieval. We test our model on tasks such as image text and text-image information retrieval using datasets like Flickr 8K, Flickr 30K, and MSCOCO captions. Our model achieves an average recall at 5 of 85.8% across all these retrieval tasks, surpassing OpenAI's CLIP model and performing similarly to EVA Clip, despite being trained on less data. For evaluating our model's text encoder, we utilize the Massive Text Embedding Benchmark, MTEB, which consists of 8 tasks across 58 datasets. While CLIP-like models typically struggle with text embedding tasks, especially in information retrieval, our model competes well with top-tier text-only embedding models, achieving an average score of 60.12%. This represents a significant improvement over other CLIP models, with an increase of around 15% overall and 22% in retrieval tasks. More detailed results can be found in the appendix.